so thanks for attending. As I briefly alluded to there, the innovation here is that we're talking about posterior mean separable costs because there already exists a paper on posterior separable costs. So that motivation is that for many economic models that we're all familiar with, from our first year in our PhD, probably even undergraduate, plenty of economic models have incomplete information. So there's private information that at least some of the agents have. And that's going to be an important component of analyzing these models. And common features of these models are that you have an order type space. You might have a high type versus a low type. And at least in many of these models, we want to have more than just binary types. We could have even potentially be a continuum of types. And that leads to some interesting features of the analysis of the model. Now, on top of this, we refine these sets of models even further. For an important class of models, what we really care about is the expected value of the type or object of the private information. So if you think about auctions, what we really care about as a bidder in the auction, our utility ex post is our type times the probability of winning the item minus the amount we pay in the canonical model of Meyerson. So if we have uncertainty about our ex post value, our utility will be given by the expected value of the object times the probability of winning minus the transfer. So it depends on our mean of, or I should say posterior mean of the type. Similarly, in trade models, if you think about Meyerson Satterthwaite, what the buyer and seller care about is their respective expected value of the item for trade. And if we think about something like financial markets, if we are a risk neutral trader, then what we care about is the expected value of the asset ex post. So these are an important class of models where we just care about the posterior mean. An important feature that sometimes is added to these models is thinking about incentives to acquire information. So maybe we don't know about the value of the type. And we need to do some learning about it, and that this could be costly. Something that's become more of interest in recent years with the development of tools to analyze these sorts of objects is the question of flexible information acquisition. Perhaps we're going to allow a wide range of signals that can be generated. It could be because there's a large number of possible sources of information, or we can think about this as a robustness exercise that we want to think about what would happen if they have access to this particular signal. How do we make sure that there's no incentive to deviate from the signal that they're acquiring? But in any case, flexible information acquisition is an important addition to these models in terms of thinking about the knowledge that the agents have of the type that's in play in these models. So what I'm going to focus on today is a particular class of cost functions for acquiring information, which I will call posterior mean separable, which states that the cost of acquiring a particular distribution of posterior means given by capital F is given by a measurable function, little c, where the cost of F is the difference between C of Z C naught, the prior mean, minus the expected value of C of Z with respect to the distribution of posterior means. Now, why is this useful? Well, we have well-developed information design techniques to analyze situations where the utilities depend just on posterior means, and we're optimizing distributions with respect to this objective function. So the net payoff in cases where we just care about posterior means and costs are posterior mean separable will just depend on posterior means. There'll be a measurable function of posterior means. And as a result, the information acquisition choice by the agent will be a single player Bayesian persuasion problem. And we know from Dvorak-Martini in JPE 2019 that the way to optimize the distribution is by finding a convex function such that tandem with the CDF of the posterior means is going to majorize the objective. So to illustrate this in a simple motivating example of a reasonable case of such a cost function, let's think about the case where the cost of information is proportional to the reduction in posterior variance. So its cost C of F is given by some scalar times the variance of the ex post variable from an ex ante perspective minus the the expected value of the variance of the ex post variable contingent on receiving a signal that tells you that the posterior mean is equal to Z. Well, we know from the law of total variance that the variance of the ex post variable from the ex ante perspective is the expected variance contingent on some other variable plus the variance of the expectation of the ex post variable given the other variable. Now, since F is a distribution of posterior means, if we know that the value of the posterior mean is Z, then the expectation of Z naught with respect to knowing that the expected posterior mean is Z is just Z itself. So as a result, we can replace in the first line the variance term with just variance of ZF. So we know that the difference in these two terms is going to be exactly variance of ZF, which is conveniently given in integral form by the integral from our lowest possible state to the highest possible state of Z minus Z naught squared. And so we can represent our little c function by negative kappa times Z minus Z naught squared. So as a result, reduction of posterior variance is an example of a cost function that is in our class. So without further ado, I'm going to go on to the model. It's a very simple model because we're not doing anything particularly complicated in terms of the decision process, and there's no game involved, so it's a pretty straightforward model. What's going to be more complicated is going to be the sort of analysis we need to verify or rationalize, as Federico said in his talk earlier today, in order to rationalize this model. Okay, so in terms of primitives of the model, all the primitives of the model are given on this slide. Both the decision maker and the analyst who's observing the decision maker's choices know the set of possible states of the world. For this talk, the set of states is going to be finite. I have an extension to a continuum of states in the paper. There's a commonly known prior CDF, F naught, with prior mean Z naught. There's a grand set of actions that menus will be drawn from in our data set, which I indicate by capital X, and the individual menus are indicated by capital A, which again, for the purposes of the talk, we'll assume are finite. I have an extension in the paper to non-finite menus. The utility of the agent conditional on the posterior mean is a function from the menu and the posterior mean to a real number. And based on this utility function, we can define the indirect utility, which is just the utility that the agent has or the decision maker has at a particular posterior mean if they are maximizing their expected utility at this posterior mean. So that we're going to indicate by phi A. Now, let's talk about the data that the analyst observes beyond this. The analyst sees all these primitives of the model. They're trying to think about what sort of process the decision maker is going through in order to generate this particular pattern of choice. So what the analyst sees beyond this is a state-dependent stochastic choice function given by sigma A, which is a conditional probability distribution from states of the world to actions. So conditional on a particular state, we'll see what's the probability that a particular action is chosen at menu capital A. Using notation, we'll also use the same sigma A for the unconditional probability of action little a being chosen, just dropping the conditional part. And we'll also define based on this the revealed posterior means, which you can think of as what the posterior means would be if the agent, or the decision maker acquires no additional information beyond what is necessary to choose with this probability conditional on the state. So if you remember from strictly increasing or convex costs of information, you don't want to acquire extra information because it's costly, and so you would always want to acquire the minimum amount of information necessary to generate a particular probability of choice. So this definition would be consistent with that you wouldn't have extra information. And so you could think about there being one particular signal at which an action is being chosen. And then at that particular action, there would be a particular posterior mean. And that would be the revealed posterior mean in the data set. Now, what we want to test is the hypothesis that the way that we're generating this pattern of data is that the decision maker is acquiring information at cost, and then based on the signal that they observe, are choosing optimally from the menu. So we are going to test the hypothesis that they're choosing a particular information structure, mu, which is a distribution over posteriors. But we don't really care about the entire distribution of posteriors. We really care about the posterior means. So we're going to, instead of focusing on mu, we're going to focus on capital F, which is a distribution of posterior means. And a requirement in order for this to be consistent with Bayes' rule is that the prior distribution, the posterior distribution has to be a mean preserving contraction of the prior. So this ensures that this is a feasible distribution of posterior means given a particular prior distribution of the variable. And this is given by the constraints that I of z has to be non-negative for all values of z between 0 and 1. So we're going to define then the set of feasible CDFs as being CDFs that satisfy this constraint. So that is our curly I set. And we will endow this set with a mean preserving spread order. So that's a partial order on the set. All right, now we also want to look that the information storage process is coming from information being costly. So we want to have some cost function of information given by capital C. I put that it could be canonical. So there's always a canonical representation of a particular cost function. A canonical cost function is one that's monotone in the Blackwell order. So more information is more costly. It's convex, so that randomizing between two distributions yields something that's less costly. And the cost of no information is 0, so that if you don't acquire any information, you're not penalized for that. Now, this will show up at some point in the paper. I don't assume this in the paper, but there's always a canonical representation of the cost function, and it's often useful to think about that, especially for immediately generating things like, choosing the real posterior mean to be optimal. If you have a canonical cost of information, then you immediately get that. Now, given the cost of information function, capital C, we are going to assume that it is, or try to test that it's separable from the decision problem itself, meaning that the utility for the decision maker is given by the difference between the expected value of the indirect utility and the cost of choosing that information. And on top of that, we're going to be testing that the cost of information is posterior-mean separable, which I showed you the formula for before. So it's a measurable function of little c. So our goal here is to provide necessary and sufficient conditions that we can rationalize the stochastic choice function by posterior-mean separable costs. However, to do so, we need to talk about some results pertaining to cost and information acquisition from previous works. And so that'll lead into the comparison and contrast with what we get here. Now, the first axiom is extremely standard in this literature. It's a sort of a workhorse axiom going back to Kaplan and Martin, 2015, called no improving action switches, which states that conditional on a particular revealed posterior mean z sigma a of a, so it's the posterior mean, revealed posterior mean for action A in menu capital A, it has to be the case that A is actually optimal at this particular revealed posterior mean. You can think of this as saying that if the decision maker is acquiring from information or is deciding based on information that they see, then their choices based on the information they receive have to actually be optimal. So this would be consistent with first getting information and then choosing based on that information. So that's basically what I say in this slide here. Now, the first axiom covers choosing based on information that you have, but we also need another axiom that states how this information arises. So that's what we're going to need a second axiom for. And to introduce that axiom, we need to show an axiom that captures the idea that the choice of information via cost of information acquisition is optimal. And this is going to be best described by contrasting it with an axiom by Tomas and Fenty, who described posterior separable costs. So not posterior mean separable, but posterior separable. So you have a cost of information acquisition, which is based on a measurable function of posteriors, and the cost is by expected difference from the prior to the posterior of the function h. And his axiom there was no improving posterior cycles. Informally, this states that if you start out with the given distribution of posteriors, then there's no way to improve the expected utility from rearranging which posteriors show up at which menu in a Bayes plausible way and increase expected utility at the same time. So his theorem is that a state-dependent stochastic choice data set satisfies no improving action switches and no improving posterior cycles if and only if it can be rationalized by a posterior separable cost function. Okay, now in terms of the difference between posterior separability and posterior mean separability, if we think about information design problems, the key distinction, if we think about in the context of flexible information acquisition, is that with posterior separability, any mean preserving spread is possible. That would be a feasible distribution of posteriors. However, with posterior mean separability, we have this extra constraint that we need to satisfy the inequality that I of z must be greater than or equal to 0 at all values of z. So this leads to different conditions in terms of optimality for the information design problem. So with posterior separability, I think everyone here is familiar with Bayesian persuasion from Kamenetz and Jenskow, which states that the way you get the optimal choice of information is by concavification. Whereas with posterior mean separability, you're going to have a convex function that characterizes the optimal choice, that you're going to have the convex function lie above the utility function. So if we think about a given utility function here with values of the state at 0, 0.4, 0.6, and 1, then the optimal information can be given by a convex function which lies above the utility function and is tangent to it at points in the support of the posterior mean distribution. So in terms of an informal distribution of my axiom, no improving posterior mean cycles, the difference from Tomas's axiom is going to be given by what's in bold here. Essentially, what we need to do is ensure that when we're thinking about switching around posterior means, we keep the points at which this mean preserving contraction constraint is binding the same. As in, we have to check perturbations where that constraint is still binding at the same points. And so this ensures that the convex function that we have from the previous slide remains the same for the different prior. And as a result, we're going to have that if we have this change of the axiom, we're going to have an equivalent theorem go through that the two axioms are equivalent to being rationalized by a posterior mean separable cost.